Okay, so why don't we get started? Few announcements. Lab 1 has been out for nearly a week. Do more than that next week. Put out the homework earlier this morning. Yes, so it's going to be due after the lab, but you need to make sure you look at it and not wait until the last minute. As I've been indicating for some time now, exam 1 is date for exam 1 is creeping up. It's going to be a week after next. Yesterday I should have confirmation on the room. Today I will send out the location and all of that. But it's basically a week after the lab. We'll have about a week to review the material. There won't be anything else happening. Okay. So those are the announcements. Just a periodic reminder to not use phones and laptops, etc. in the class. That's our usual policy. And most of you have been respecting that, so thank you for that. So I will, since it's Thursday, start with the computing parable as I said I would occasionally. So this one is going to be on the lost key. So the story goes as follows. There is a drunk person looking for something on the road under a light post. And he looks and looks, and then a person comes along and asks him, "What are you looking for?" So he says, "I lost my key." So then the guy said, "Okay, let me help you." And then both of them look for the key. And after some time, they don't find it. So then the guy asks the drunk, saying, "Are you sure you lost it there?" So he says, "No, I did not, but I lost it over there." And he points to a different part of the road. Then the guy says, "So why are you looking for it here?" He says, "There is more light here." Okay, so what does this mean? What's the takeaway? The takeaway is to actually focus on things that matter and not just follow what seems like the easy path of where there is seems like the grass is greener. Okay, so that's the computing parable of the week. So we will start the lecture with that. We were talking about locks last time and synchronization. I'm going to continue that discussion. We will wrap up locks today, and I will also discuss semaphores, which is the next synchronization. Okay, so this is just a recap. So last time I defined all these important terms that you should be familiar with: synchronization, mutual exclusion, critical section, and then we came to locks. Synchronization essentially means the ability for threads or processes to cooperate on a task. Okay. What mutual exclusion means is the ability of again a thread or a process to perform some task and exclude other threads and processes from performing the same task at that point in time. We are excluding other entities, in this case threads or processes, from performing a certain task. That's called mutual exclusion. Okay? And critical section is a piece of code that only one process or thread can execute at any given time. One thread in this case can execute at any given time. Critical sections are implemented using mutual exclusion. The way only one thread can execute it is you use mutual exclusion to prevent other threads from executing that code when the first thread that is doing it is, or first thread is executing. Okay? Locks are a primitive that allow you to implement synchronization through mutual exclusion, and when you protect a piece of code using a lock, that piece of code becomes a critical section. Okay? We looked at the primitive, so lock has two methods, okay? Acquire and release. And the basic rules are always acquire the lock before entering the critical section, always release the lock when you exit the critical section. When you initialize the lock, it's set to free. Okay, so that's the basic idea. We looked at how to do too much milk with locks. I'm not going to go through that. What I want to do now is to show you how you can implement locks. Okay, so the goal is not just to understand how to use locks in your code, but this is a course on operating systems. So we should also try to understand what locks are internally, how they're implemented. Okay, so to do this, we'll have to understand what kind of hardware features are available to us and how to use them. So the tools that we will use are enabling and disabling interrupts and test and set. Okay, so let me first talk about enabling and disabling interrupts. Okay, so the basic idea is The reason you may actually have problems when you implement synchronization, as we looked at the too much milk example, is thread A is executing. Okay? Something happens, a time slice expires. So it has to suspend execution, relinquish the CPU. Some other thread could run and do something that thread A was supposed to do, and then things go wrong. Okay? That's really the problem we're trying to avoid. Okay? One way to avoid this problem is when a thread is in a critical section, you temporarily disable whatever might cause the thread to for its execution to be interrupted. Okay? So you could do this by disabling interrupts, because an interrupt can occur at any time, and that can cause the thread to whatever is executing to suspend execution, and then you jump into the OS interrupt service routine and so on. Okay. The other thing that could happen is your time slice may expire, and the timer goes off, so then some other thread gets to run. So if you could prevent both of these things from happening in your implementation of a lock, you can now implement critical section. Okay. And that's essentially what we are trying to do here. So what is mentioned here is there are two ways the scheduler gets to run. There are interrupts, and then there are, you could also do I/O, incidentally. That can also make you give up the CPU. But the I/O part you can control. Inside a critical section, you may not want to put I/O instructions. That's one way to avoid it. Okay? So what we are going to do is, by disabling interrupts, prevent the CPU scheduler from running, and if an actual interrupt occurs, you are going to mask it temporarily. You are not going to suspend execution. You can queue the interrupt or ignore it altogether. Okay? So that's the basic idea. And here is an implementation. This is pseudocode, but it's implementation of a lock. Okay? Using this notion of enabling and disabling interrupt, you'll see that this is the class that has two public methods, acquire and release. Okay, internally, we are going to have a value that tells you what is the current state of the lock. Is the lock available or is it in use? Okay, so this is a binary variable. Okay, this is not a binary variable, but you can think of it as a binary variable. Okay, and you see that there is also a queue that is basically going to be maintained internally, which will queue up all the threads that are called lock acquire but have been waiting because the lock is in use. Okay, so we look at how to use it. So here is the constructor. Okay, so you set the lock to 0, which is saying it's free. That queue that we talked about is initially empty. Yeah, this is your acquire method, that's the release method. And it's fairly straightforward. What you're going to do is, when you call lock acquire, you're first going to disable interrupts. Okay? So now what has happened is, then you check, is the lock in use or is it free? If the lock is free, then you say that you have the lock, okay? And then you let the thread execute. Okay? If the lock is busy, okay, meaning that it's in use, you are going to make the thread wait. Okay? You are going to add the thread to the queue for the lock, which says that the thread is waiting, and you put the thread to sleep. Okay? So this causes the thread to wait until the lock becomes available at some subsequent point in time. Okay? So that's basically what you will have to do inside a lock acquire method. Okay? You have to check the value of the lock. If the lock is available, you grant the lock. The lock is not available, then you are going to have to make the thread wait. Okay? Then the way you make it wait is, rather than making it busy wait, you will add it to a queue. This is a wait queue. Okay? Just as we have I/O wait queues, now you see that there is a wait queue for lock. Okay? This is a wait queue for a synchronization protocol. Okay? So you add it to the wait queue and you essentially make the thread sleep. Okay? This is what the OS of the library that's implementing a lock will do, not do the program. You simply call lock acquire. This is a pseudocode for an implementation of an acquire method that uses disabling of interrupts. Okay? And here is lock release. What you're going to do is you're going to check whenever a lock is being released by a thread, you go and examine the queue and ask, are there any threads that try to acquire the lock while the lock was busy? Okay? So if the answer is yes, the queue will be non-empty. There will be threads on this queue. Okay? So if the queue is non-empty, you take a thread on the queue and then say you have the lock. So you can basically put the thread on the ready queue so that now it's ready to execute it as the lock. Okay? And the CPU will execute it at some later time. And if the queue is empty, that means no other threads want the lock, you just set the lock value to be free. Okay? So at a later time, some other thread can acquire the lock. Okay, is that clear what a simple implementation of a lock looks like? Any questions on this? I'm going to show you a different implementation that doesn't depend on disabling interrupts. Disabling interrupts is a very strong measure you take and it causes problems in the hardware. If a very important interrupt comes along, you have disabled the interrupts altogether of the system. Okay, this may cause you to miss events that may have occurred and so on. So typically you do not implement locks in this fashion, but it is a way to do it. Yeah, there's no issue with correctness, but it would cause other problems because you are taking a strong measure and says all interrupts are going to be disabled temporarily, no matter how important they are. Next question there.
So by disabling interrupts, that also mean that the time slice can expire, or can the time slice still expire in a different process?
Yeah, so the question is, when you disable interrupts, can the time slice expire? So the time slice will expire, that will cause the timer to go off. Timer going off is an interrupt which we have disabled. So the time slice ends, but the CPU scheduler doesn't know it has ended because it's waiting for the timer to tell it that the time slice has expired. So you're essentially going to ignore the expiration of the time slice and let this thread continue to run. That's the other problem with disabling interrupts, right? If you have a long critical section, by disabling interrupts, you are going to let the thread run for a while until you re-enable the interrupts at least. Okay. So there are multiple ways to do this. This is one of the problems.
So for that pass build example,
yes,
we can make that work by disabling interrupts and enabling interrupts.
Yes. So I think there are two ways to answer the question. Maybe I should clarify this. So yes, you could certainly disable interrupts because what that does is only one thread gets to run by default. That's the thread that's executing. It's never going to be kicked off the CPU, so you can run the whole time. So no other thread can look for the state of the fridge and so on. And then once you're done, you can re-enable it. That's one way to do it. Now, I should mention, however, here that we are not disabling interrupts for the entire critical section. We are only disabling interrupts for the lock acquire part of the code. Okay, so I mean, this is only within the acquire part of it. So that's a slight distinction. So only the acquire and release method are atomic in that nothing else is happening. So the state of the lock is cleanly checked and set to either free or in use in this method. Okay. Now you should try to understand why you don't need to disable interrupts for the entire critical section. That's one way to implement things as well. You take a critical section, you disable interrupts for the whole time, and a thread will get to run for the entire critical section. But that will cause problems like interrupts will be ignored, no matter how important. Time slices expiring will also be ignored. So this thread can have a free run on the CPU for as long as the critical section lasts. Right? A better way to do it is to only disable interrupts. You can see that you're re-enabling interrupts here within the acquire and release method. So what this does is, since you're guaranteed that every thread is going to call the acquire method before entering the critical section, the acquire method will block all the threads that cannot grab the lock. So you don't need to explicitly mask interrupts for the entire critical section. Okay, so you only do it while you are acquiring the lock, then you re-enable interrupts. Okay? Let time slices expire. The thread that holds the lock will get descheduled. Some other thread will run. If it calls lock acquire, it will be immediately put to sleep. So it cannot enter the critical section in any case. Okay, is that distinction clear? Okay, a crude way to implement it is to disable and enable interrupt for the entire critical section. A better way to do it is to enable and disable interrupt only in the acquire method, because this method has to be atomic. You cannot have something else interrupt the CPU and while you are in the middle of changing the lock state, because something else could call the lock acquire and bad things can happen. Okay? So you are only protecting the acquire method, not the entire critical section. It's an important distinction. Are there questions on this before I move on? I'm going to show you a different implementation that doesn't depend on disabling interrupts. Okay, so the takeaway is, if you're OS designer, occasionally if you actually look at kernel code, you will see that there are parts of the code where the kernel cannot be interrupted, where things are happening that are so important that nothing else can run. And if you're doing some very critical operations, then you are okay with disabling interrupts, and you should do it for as little time as possible, because, as I said, disabling interrupts is a fairly strong measure. If something happens, like a network packet arrives, okay, that raises an interrupt. If you ignore it, then the packet is not going to get processed. Okay? Or worse, there is a signal alarm from the CPU saying machine is overheating. The battery in your laptop is critically low. You ignore it, the battery will die, and then your OS will lose all of its state rather than saving it. So there are important reasons you should only do this for very short periods of time. Yeah, so this is okay, one way to do it, but you can do better. Any questions on this? Okay, so I'm going to show you a different way to implement lock. So this is by far the preferred way, not the technique I just showed you with this friend on enabling a disagreement. So this technique uses what are called atomic instructions that are specially supported by the CPU precisely to implement synchronization. So most modern CPUs will have special assembly instructions, okay, of which test and set is one example, but there are many others. Okay, so the special CPU instruction that have been put in place simply to allow you to implement things like locks and semaphores in an atomic fashion. And that's what we are going to look at. The canonical example of such an instruction is test and set. Okay. In x86, which is all Intel architectures, there is a variant of test and set which is called exchange. In yet other architectures, if you look at RISC architecture, there's something called compare and search. They by and large do the same thing. Okay. So I'm going to only use one rather than explaining how to do it with each of those. We'll just use one. We'll use the test and set instruction as an example. We'll understand what this is, what it does, and then we'll see how to implement locks. Okay. So what is a test and set instruction? So in a test and set instruction, you specify an operand, a value, a register, or a memory address. Okay. You can use a memory address. So you can say test and set variable I. Okay. So you specify a variable I. Okay. What the instruction does, this is an assembly instruction. So the instruction in one single instruction is going to check the value of I, okay, read it, check meaning you read the value of I, okay, and you write 1 to I. Okay, you set the value to I in one instruction. Typically, this would require multiple instructions. You would have read I, okay, and you have written 1 to I. Okay, so all of these multiple instructions in test and set are collapsed into a single atomic instruction. So this whole instruction is going to be in one instruction or in one cycle. Is going to read the value and return it and write 1 back. Okay, that's what it does. Now, how we use it, we will see. But is that clear what the assembly instruction is doing here? Okay, so this is used supported by most uniprocessors. Multiprocessors complicate all of this. So we won't look at the multiprocessor world here. But let's assume we are in the uniprocessor world. Okay. So now you have this assembly instruction, right? What is it doing? It's you specify a variable, typically an integer variable. It reads the value and returns it, and then sets it to 1. So how do we use this to do locks? So here is an implementation of locks with test and set. Okay, so you'll see that it's a very small implementation. So you'll have the same lock acquired in these methods, okay, and you have a value which you are going to initialize to 0, which indicates lock is free. Okay. And then the acquire method is now essentially a while loop on the test and set. Okay. It's a single instruction. All that is saying is while test and set of value is 1, okay, just sit in the while. Okay, so what is test and set doing? It's basically checking the value, okay, and returning the value. So if the value ends up being 1, yeah, meaning that the lock is in use, it's going to basically return 1 and then you sit in the while, not exit the while. Okay. Now initially the value is 0. Okay. So if you initialize it to 0, the first thread that is going to call acquire, okay, will basically test that condition and it will end up being false. You will do test and set on value, you read the value, and it's going to be 0. 0 is not equal to 1 obviously, so the condition will fail, so we'll exit the while loop and you set the value to 1 in one atomic instruction. Okay, so the first thread that calls acquire will read the value, set it to 1 and then enter the acquire method. Or exit the acquire method rather, meaning you acquired the lock. Any subsequent thread is going to sit there and loop until the lock is actually released. Because now the value is set to not free, so you're just going to sit and loop. Because every time you're seeing that the value is 1, so you sit there, you cannot exit. Okay, so now that's acquired. Let's try to understand why this is actually going to work for us. Okay, so first it should be clear that only one thread can acquire the lock at any given time. Is that clear? Yes? Not clear, you should say so. Okay, so let me ask, why is it that only one thread can acquire the lock? Why can't two threads acquire the lock? Yes.
Because testing and setting happens at the same time as long as it's scheduled.
Sorry, can you speak up a little?
Because testing and setting happens at the same time as long as it's scheduled.
Okay, so test and set. So remember that test and set is a single instruction. Okay, so first time you should realize that the first thread gets to enter the critical section. Because initially, what's the lock value? You don't speak up.
Lock value starts at 0.
Value starts at 0. That's the constructor, right? 0 means lock is free. 1 means lock is in use. Initially, value is 0. Okay? What happens in the acquire method? You're going to go and say while test and set of value. Okay? So that test and set, think of it as a function that's going to return the value of the parameter and set it to 1 inside the function. It's actually an assembly instruction, but that's what it is doing. Okay? So it is going to return what's the correct value. It's going to say value is 0, so test and set will return 0, and it has now set the value to 1. Okay? So that while condition is going to fail. Because test and set has just returned 0, and we are asking if test and set equals 1, which it is not in this case. Okay? So the first thread is going to basically going to acquire, set the value to 1, which means it's in use, and you basically acquired the lock. So now you've got into your critical section. Okay? So if you now think about the too much milk problem, which was several slides ago. So you basically call lock acquire. The first thread that says thread A, initially lock was free, so it will exit the acquire method and go into the critical section and start doing whatever it needs to do. Okay. Now, if thread B comes along while you are in the acquire in the critical section, you call acquire, you are going to go and check do test and set. At that point, the value of the lock is 1. Okay, so you will sit in the while loop spinning. So you will say, what's the value? Value is 1. You also set it to 1, so value doesn't change. So you are going to just sit there and spin. So you will be in the acquire method and just sit spinning in a while loop while this thread is doing whatever it needs to do inside the critical section. Okay, yes, question.
Might it be a little expensive to keep all those threads that are waiting active and just going through the while again and again instead of putting them to sleep?
Yes, good point. So point is, isn't it expensive to sit and spin in a while loop? All the threads that are calling acquire will sit and spin them. Just check the value. Value is 1. You keep doing this over and over. Okay, so this is indeed a problem. This is called busy waiting. I introduced this term a few classes back, maybe 2 classes ago. Because we will see that this is a correct implementation but not an efficient one. Okay? But it's a very simple implementation. So we'll try to do better than this in just a moment. Okay? So first let's try to make sure you understand why this even works. Okay? So you will see that the release method is very straightforward. In lock release, you reset the value. Say lock is free. Okay? As soon as you reset the value to free, any thread the first thread that subsequently does test and set is immediately going to get the lock at that point. So you will do test and set the thread that had the lock set it to 0. So now test and set is going to return 0 and set the value to 1. So that our next thread that executed that while loop gets to go next. And any other threads that are still spinning will continue to spin because the lock was immediately grabbed by the first thread that did test and set after the lock was released. Okay? That clear? So that's lock acquire and lock release. Okay? It's a very straightforward implementation. Now we should ask the question: why did we need an atomic instruction? Couldn't you have written a test and set function that was 2 lines of C code or Java code that said return the value of whatever that value is and set it to 1? Okay, why couldn't you have done that?
Because that's not
Okay, so yes, that's not atomic, but what does it do? It's not atomic. So I'm going to write a function and ask you why couldn't you have done this instead of depending on This is what your assembly instruction is doing. It's checking the value. If the value is 0, it sets it to 1 and it returns 0. Otherwise, you basically return 1 because the value is already 1. Okay? So rather than depending on an assembly instruction, if you had done this, what would have happened?
Well, isn't that like leaving a note where you can leave the note but then get these schedules from the, I mean, it's like checking and then after you check loop, so you get into the if loop and then the other thread can come along and get in and then they can both do it and get too much milk.
Okay. So the point that is being made is if that instruction is atomic, it's one assembly instruction. This is actually a set of assembly instructions. Okay? So you can ask what anything could happen while the instruction is executing. In particular, your timer may expire and you may get descheduled. Okay? Now you should realize that when you have one instruction, you always get descheduled at the end of the instruction, not in the middle. Okay? This is important. So you cannot actually have timers going off and you are evicted from the CPU in the middle of an assembly instruction. You have to at least finish the instruction and then get descheduled. So if you already started executing, you are going to finish before you get kicked off. Okay? So you have finished all of these tasks and then you get descheduled. But if this was a function, not an assembly instruction, you could get descheduled anywhere in between because this is a set of, this C code or Java code will be translated into a set of assembly instructions that do those tasks. So you could be evicted in the middle and then all sorts of things can go wrong. It's the same as what was pointed out. This is essentially the task of I check the note. If there is no note, I leave a note. Okay, so your value is saying if the value is 0, I set the value to 1. Right? So all of the things that could have gone wrong that we looked at in the 2 mechanic example will go wrong here. This was a function, not an assembly instruction. Okay, because you will get descheduled, might get descheduled in the middle, and then you will have multiple threads in acquire, and that's a bad thing. Okay, so by having a single assembly instruction that does this, you are actually going to be able to do this accounting. And the important thing is, even if the time step expires in the middle of that instruction, the CPU always waits until any instruction that is currently executing is finished. So you can't have half an instruction. You can either have the full instruction or nothing. If it expires at the beginning, you will actually get descheduled even before you started. That's okay. You never executed the thing at all. And if you are in the middle, you will wait until you finish. That's the important thing. Okay, is this clear? Okay, so this is an implementation that is going to use test and set. Now we'll come to that point that was raised here, which was this whole problem of busy waiting. Okay, so we said, okay, so this implementation is going to work. There's no problem with it, but it's not an efficient implementation. Okay? And you would ask, so why is it not efficient? This while loop essentially just keeps on checking the value. Okay? And if the value is 1, it's going to keep repeatedly doing the same thing over and over again. Okay? And that's going to waste CPU cycle. As was pointed out, a better way to do it is if the lock is in use rather than sitting and checking the value over and over again, wasting CPU cycles, put the thread to sleep and wake it up when the lock actually becomes free, as you have done in the disabling interrupts and enabling interrupts implementation. So busy waiting is to be avoided as much as possible. Okay, because it's going to simply make all the threads that are in acquire just sit and spin in a loop, doing nothing but consume CPU cycles, which you can avoid. Okay, so then the question is, can we come up with a better implementation? So we will now look at a different implementation of locks that also use test and set. Okay, and this is an implementation with what is called minimum busy waiting. We cannot get rid of busy wait because this test and set you have to keep checking. But we'll try to not spend all of the cycle. We'll try to reduce the amount of busy wait that you can actually have busy wait that you have. So here is different implementation. This is a little more complicated. It does the same thing, but a little more complicated. So your lock acquire, lock release. Okay. So what you are going to do is rather than use the test and set to check the value of the lock, you are going to use test and set to basically guard the function itself. Okay. So what you will do is you will basically put this while loop here which says while test and set guard is 1, sit and spin. What this simply does is it only lets one thread go into the function at any given time. Okay. So initially you set the guard value to 0. The first thread that calls acquire will basically check the value of guard, it's 0, so it will immediately exit the while loop and start executing the call. Any subsequent threads that come along will sit and spin them. Okay, that's the first thing. So now we'll see why that's minimum busy wait in just a moment. Let's finish the acquire. So here you are now going to check. If the value is not free, then you basically put the thread to R2 and put it to sleep. Okay? So you're simply going to now say, I check the value of the lock. If the lock is in use, put the thread to sleep. Okay, put it on the queue. And if the value is free, then you're going to say that there's nothing to do. You set the value to busy, okay, and then you set reset the guard. And here is the release. You again have a guard function here, and we'll see what that does. Again, this also means that a function can only one thread can be acquiring, release, or acquire at any given time. Okay? But then, what does the actual function? You check the queue. You're trying to release the lock. So first, you're going to see is there any other thread that requested the lock in the meantime. If so, it would have input on the queue. So the queue would be non-empty, so you check the queue. If the queue is non-empty, you take the first thread in the queue and say, here is your lock. And then you put it on the ready queue. If there are no threads waiting, you are going to set the lock to free. Okay. Now let's ask the question, what did that while do? And why did it reduce the amount of busy? Clearly, that's also busy wait, as you can imagine, sitting in a while loop and spinning. But the claim is that you reduce the amount of busy waiting in this implementation over the previous one.
Because now you made kind of a critical section out of the checking block, so that not only you're only checking much less frequently and just waiting for it to go.
Okay. Anybody else have any comments to add or anything to say? Yes.
On average, the amount of times, or the amount of times that spend stages that were reduced in that once the fire record, well, once it's finished, send the value, eventually that value is going to return the card.
Value is 0.
Allowing one to go through and start the process. So on average, you'll see less free time, but in the worst case, all the threads go through and get to that point.
Okay. You have something else to say?
Just reduce the amount of spins, so just
You have to speak up a little bit.
doesn't it just reduce the amount of spins? Basically, if you go through, it either goes to the tip or the else.
Okay. So all three of you have said essentially the same thing in different ways. So I'm going to show you. Let's keep that. Okay, so if you just look at too much milk, we said. Okay, so this was the too much milk problem. Okay. If you look at the first implementation of lock, not the one that we said. So here, when you call acquire, okay, in this implementation, if the lock is in use, you are going to sit and spin while other threads execute the whole critical section. Okay, this critical section could be of arbitrary size, because this is a very simple synchronization problem, but you could have more complicated ones where there could be several statements within the lock acquire and lock release. Okay? So this could take an arbitrary amount of time, and all the threads are sitting and spinning in the lock acquire except the first one that called it. Okay? So until the first thread executes this arbitrary size piece of code. So you are busy waiting for over the entire critical section in the first implementation. Now in the second implementation, which I just showed you, okay, you are actually busy waiting only when you implement or only when you execute acquire, not while you are in the critical section, because you are only looking for this guard statement, and the guard statement is reset when you exit. Okay. So you are only protecting the acquire method with your test and set instruction and making that atomic. Okay, the reason you can afford to do that is all other threads have been put to sleep, so they don't need to check the guard while the first thread is executing the critical section. So they're different implementation. Okay? So in this case, you are only executing the busy wait within this method while the first thread is executing this method. In the previous implementation, you execute busy wait for the entire time. Okay? So the amount of time over which you are going to do busy wait is dramatically reduced in this implementation. Okay? Because of the way we have done it, we are only trying to ensure that one thread can be acquired at any given time. And you just go and change the value of the lock. The lock is not free, and you just put this thread to sleep. And that's all you need to do. And then it doesn't need to busy wait anymore. It's already put to sleep, so you set the guard to 0. Okay, so you have shrunk the time and the amount of code over which you have to do busy wait. The first implementation, busy wait over the entire critical section. Second implementation, busy wait only within the lock and release methods, not the whole critical section. Okay, so two different implementations, which have sort of two different amounts of busy waiting. This is more efficient. It still has busy waiting. It's not it's not gotten rid of it, but you have reduced it as much as possible. Okay, you are going to waste far less cycles in this case. Any questions here? Yes, question.
How about like additive interrupts?
How about what?
Additive interrupts.
So what about other threads that are not calling lock and lock?
Like, how does it disable the interrupts?
How does it disable the interrupt? So this implementation uses test and set instruction. You don't need to disable interrupt. There are two different implementations. We have gone through 3 implementations of locks so far. One that enables and disables interrupts. When you have test and set, you don't have to do anything with interrupts. Okay? An interrupt can occur in the middle of this lock acquire. That's okay. Because test and set is atomic. We just said that. Right? So this, you are not doing this. You don't have a function. You have an atomic instruction that does that. So even if an interrupt occurs, you wait for the test and set to complete. That's one assembly instruction. Then you go process with interrupt. So you cannot be interrupted in the midst of an instruction. That's what we are banking on in this case.
This can interrupt in the if else.
Yes, so you can be interrupted in the if and else. You cannot time slices expire in the if and else. All that is okay. Because the first statement here is a guard. No other thread can actually enter. The first thread that enters the acquire is going to essentially be the only thread that is executing it. Even if your time slice expires, something else runs in the midst, you are going to, those threads will be blocked here. They cannot enter. That's why you are safe. So the guard is protecting the function.
So is the thread that calls acquire pass itself in? This is acquire thread.
The question is the thread that acquire pass itself in. So typically this will be implemented as a system call. This code is actually taken from a toy operating system, which is why you see some things that are not true in practice. If you call a system call, the OS is executing this. Okay, so the OS can put the thread to sleep and reset the guards and do all of that. There's some question that is.
The else block of the acquire method should the guard be switched to 1 because this implementation
So you are saying should you set the guard to 1 here? Is that your question?
Yes.
So initially guard is 0. When you enter the acquire, you set guard to 1. When you set guard to 1, you're preventing any other thread from entering. Test and set has set it to 1 because this is the implementation of test and set. Okay, so in one assembly instruction, that's what test and set does. Right, so in one instruction, so you will see what it does. So it reads the value and it writes 1 back to memory in one instruction. So test and set itself has set it to 1. So you don't need to do it explicitly. Yeah. So that is the whole point of test and set. What would be normally multiple instructions is being done in one assembly instruction. That's a special instruction that the CPU supports to make all of this work. Any other questions on this? Okay, so I'm going to now switch gears and talk about different synchronization primitives. Okay, so we finished locks. It's a very straightforward primitive that allows you to write code with critical section. Okay. Now we are going to look at another one, and then next time we will see yet another one called monitors. Okay, so this one is called semaphores. One way to think of this is it's a generalization of locks. You can do everything a lock can do. There are certain things that are harder to do in locks that semaphores make it very easy. Okay. So we look at what they are. Okay. So semaphores are basically generalized locks. They are also special integer variables, and not your typical usual integer variable. They are special kinds of integer variables whose values can only be changed atomically, as you will see. Okay? And they support, like locks, they support two methods. Just as there's a lock acquire and lock release, you'll see that there is a method called semaphore wait and semaphore signal. Okay? And we'll see what they all do in just a second. But as an aside, you should know that they were invented by a famous computer scientist named Dijkstra, who also wrote one of the very early operating systems back in the 50s called the BFD operating system. So he was responsible for coming up with this whole idea that you need synchronization, and introduced this notion called semaphore, saying here's a good way to implement synchronization when you have things like threads and so on. So a lot of this ideas go back to the late 50s, early 60s, okay, in the days of Dijkstra when he came up with some of these ideas. Okay. So now with that background, let me talk a little bit about what are semaphores, okay, and how they work. So as I said, semaphores are simply an integer variable that can be updated incremented or decremented using two special methods. Okay. So there is a method called signal that is going to decrement it, and there's a method called wait that's going to increment it. We'll see those in just a moment. Okay. But also, you can have two types of semaphores. Okay. There's something called a binary semaphore or a mutex semaphore, which is exactly the same as a lock. It does more or less the same thing. And as the name binary semaphore indicates, when you have binary semaphore, the value of the semaphore is either 0 or 1. Just as in lock, it was 0 or 1. Okay? And in counting semaphores, which is generalization, the value of the semaphore can go from 1 to n. Okay? It is either used to protect multiple instances of a resource, or as we will see, you can use it to implement special types of scheduling. You can tell the thread saying thread 1 goes first and thread 2 go next and thread 3 goes next. So you can implement code that actually explicitly enforces these constraints. That's a very important point that we will look at, because otherwise semaphores do nothing different from a lock. There is no reason to have one more primitive that does the same. Okay? So semaphores do something more than what locks can do, and we'll look at that as well. Okay, so have you done semaphores in 230 or did you do locks? You did semaphores. Did you do counting semaphores or just binary semaphores? Sorry, somebody said something. Okay. So we'll see how to use them in some interesting ways, but let's start with the simple concepts first. Okay? Regardless of whether you are doing mutex semaphores or counting semaphores, you have a semaphore which all semaphores have only two methods, wait and signal. Okay? So the typical way to use a semaphore is you call wait at the beginning of a critical section, you call signal at the end of a critical section. Okay? So in this case, wait is more or less equivalent to lock acquire, and signal is more or less equivalent to lock release. Okay? So what wait will do is the first thread that calls wait will get to enter the critical section. Any subsequent thread that calls wait will be blocked within wait. Okay? So this is basically how things are going to work. So I'll show you that what the wait and signal do. Okay, so here is an example that shows how to implement too much milk. Okay, so you will see that it's basically analogous. So as I said, instead of lock acquire, you simply replace it by wait, and lock release, you simply replace it by signal, and then the middle part is the same. Okay, so in this scenario, they are doing something very similar to locks. Okay, and here is basically the definition of wait and signal. So what wait does is you check if the semaphore is free, which means it's non-zero, its value is non-zero, you will basically let the thread continue, you won't block it. But if the value of the semaphore is 0 or in some cases negative, you are going to block the thread. Okay, so all that wait is going to do is atomically check the value of the semaphore. The value of the semaphore is non-zero and positive, you enter the critical section. The value of the thread is value of the semaphore is 0, okay, then you block the thread. And release is going to unblock the process if there is one waiting on the wait queue of the semaphore. It's somewhat similar to what logs would do. Okay, so this is too much milk. I already said that. So here is an implementation of signal and wait, and this implementation works regardless of whether you're binary or counting semaphore. It's a general implementation. Okay? It's not going to depend on any particular type of semaphore. So here now I'm not going to show you any implementation that explicitly uses interrupts or test and set. We know how to do that. We are simply going to look at pseudocode and assume that either you disabled interrupts at the beginning or you are going to implement some of these checks using test and set. Okay? So I'm going to simply present higher level pseudocode that defines what wait and signal do. But I'm not going to insert test and set instructions in this pseudocode. Okay? But you be aware that you still have to ensure that they are found. So you have two public methods, wait and signal. Okay? There is a value and then there is a queue. So the value is initially set to whatever the constructor calls. So you can, unlike in logs, where the value is always free, okay? Semaphores allow you the flexibility of setting the value to whatever you want. You can set it to use, set it to free, and by doing so, you see, you can do interesting things. When you are using the semaphore as a straightforward log, you are going to set the value to be free, just as you did for a log. Okay? So, basic point is the constructor for a semaphore. When you declare a semaphore, you can pass whatever initialization value you want to set the semaphore. Okay? In logs, you always set the log to free initially. Never set the log to use. But in semaphore, you can pass a value that can set it to whatever you want. Okay? And here is the implementation of wait and signal. Okay? So wait essentially atomically decrements the value of the integer variable. Okay, so you will see that value has been decremented by 1. And then you check, is the value less than 0? If the values are negative, the value is negative, then you are going to add the process of thread to a queue, wait queue, and then block or put the thread to sleep. Okay, all of that is done atomically, so I have not shown you the test and set part. But the high level pseudocode is when you call wait decrements, check if it's negative, you block. If it's not negative, then you basically let the thread continue. Signal is going to do the opposite. You will increment. So signal is equal to incrementing this integer variable. So first you always increment, and if the value is less than or equal to 0, you will look at the queue. That indicates that the queue is actually not empty. You will take the first thread or process of the queue, and you will give it the semaphore. Okay, so this is going to ensure that depending on the value, only one thread or process can enter the critical section if you are using it as a binary semaphore. Yes, question. You're asking, this should be greater than or equal to 0? No, it should be less than. I should show you examples of what happens. Okay, so is this clear? I'm going to run through some examples and we'll see what happens in each of these cases. Okay, so now we are going to look at some snippets of code and see what happens to the value of the semaphore and the process of thread going to block or not whenever it calls wait. Okay, so this is the first example. So we are going to, in this case, set the value to 2. We will initialize the value to 2. Initially the queue is empty. There is nothing blocked. And then that's the code that process 1 is going to call, that's the code that process 2 is going to call. It's going to call wait twice at 2 signals, and in process 2 you are going to call 1 wait and 1 signal. Why you are calling 2 waits, that's not very important. Okay? All we are trying to do is understand that what is the value of the semaphore and what causes the process to block, or which process is blocked and which process is don't block. And to understand that, you simply have to blindly execute this code that I just showed you, and I'll tell you what's happening. Okay? So let's start. So let's assume that's the order in which the instructions execute. Okay? So P1's wait executes first, and P2 executes the wait, and P1 executes its third wait, and so on. And then the question is, what is going to happen to the value, and is each of these processes blocked or printed? So it's a simple example. Let's run through this. So let's see what happens. First time you call wait. Okay, what does wait do to the value? You are going to decrement the value. Okay, so each of these. That's what I showed you here. So the pseudocode says decrement the value and then check the value. The value went negative, block the process. So very straightforward. So always you decrement and see what is the value. If the value is negative, you block. Otherwise, you don't block. Okay. So now the value is decremented from 2 to 1. Okay. So P1 decremented, the value has become 1. Okay. 1 is not negative yet. So you're going to let P1 execute. Meaning that wait is not going to block it, it's simply decremented it and let it continue. If Q is empty, still. P2 is now going to call its wait. You are going to decrement again. So what's the value? The value is gone to 0, not negative yet. Okay. So you say 0, that is negative, not negative, so you are going to execute. So Q is still empty, P1 is executing, not blocked, P2 also is not going to block. We call this wait. Okay? So we have gone through 2 waits. Nothing is blocked yet. Okay? P1 is going to call its second wait. Okay? So P1 had 2 waits. You see, P1 is going to call its second wait. Now the value goes to negative 1. Okay? So we are going to check, execute that function. Okay? So which is going to say, if the value is negative, which it now is, okay, you are going to add the process to a wait queue for the semaphore and block the process. Okay? So now, after you execute the third wait, in this case, the value here, value is gone negative. Okay? And then you block this process. So P1 is going to go on to the queue. Okay, the queue is no longer empty. You put P1 on the queue, P1 is now blocked, it's on the wait queue, P2 will continue to execute. Is that clear? What's happening? We are simply blindly executing the code to see what's happening. If you have that implementation of a semaphore and you have written this code, okay, what will happen to each of the processes? Okay, now let's continue. If P2 is now going to call signal. Okay, signal, what does signal do? Signal increments. Okay. Wait decrement, signal increment. So we are going to increment the value, it's going to go from -1 back to 0. Okay? And then you can just go back to the pseudocode. You will see that you check the value after you incremented it. Value is value plus 1, so it went to 0. You say is value less than or equal to 0. Okay, it is, it's currently 0. That tells you the queue is still non-empty. So you are going to remove the process that's in the queue, which was P1. It's been taken off the queue and it's going to be woken up. Okay, meaning it's going to be put on the queue. Okay, so now we go back to the example here. Okay. When you do P2 signal, value has gone back to 0. Q is again empty because you took P1 off the queue. Okay, P1 is now going to be ready to execute. P2 is actually executing. Okay. Now these 2 subsequent signals are going to continue to increment the value. Value is going to go back from 0 to 1 and from 1 to 2. Q is empty, so there's nothing to do. You just check that Q is empty and then you just leave it as is. So P1 and P2 continue to execute. Okay, so this is just a simple simulation of what a semaphore is trying to do this process. What we achieved, we don't know. This is just some code that we are simply blindly executing to see what the semaphore does to the processes. Okay, we'll actually try to do something useful with semaphores. Is this clear? Alright, so there is another one which I'm going to ignore here. You can just run through this and see what happened. Let's try to actually use semaphores to do something useful. Okay, so you can use semaphores to do one of 2 things. You can use it to implement mutual exclusion. If you use semaphores in this mode, you're simply using the semaphore as a lock. Okay? You could have used locks, but let's say for whatever reason, your library only supports semaphores, not locks. So you can use a semaphore as a lock. It does nothing different. It's exactly the same thing. And to use it as a lock, all you need to do is initialize the semaphore to value 1. I said semaphores are constructors, you can initialize it to whatever you want. So if we declare a semaphore and set it to 1 initially, you basically have a lock. Okay, this is also called a binary semaphore. So what does this do? First time some thread calls a wait, we will decrement it to 0. That thread is going to continue executing. Okay. Next time another thread calls wait, the value goes negative, immediately that thread is blocked. Any subsequent threads are blocked as well. So that tells you that only one thread can enter the critical section. Okay. That's the thread that decremented the value from 1 to 0 the very first time. Okay, is that clear? Yes. Binary answer. Show you some code. So the basic rules are, if you want to use the semaphore as a lock, set its value to 1, protect your critical section with a wait and a signal. Okay? Use wait when you enter the critical section, use release when you exit the critical section. And you basically have a semaphore that's behaving like a lock. Okay? But you can use the semaphores to do more interesting things, which is you can explicitly implement what are called scheduling constraints. Scheduling constraints say, if you want to guarantee that threads execute some code in a certain order, that thread A executes some code first, and then you explicitly tell thread B to execute the code next, you can use semaphores to do that. Important thing to realize is, when you use semaphores to do that, it doesn't matter what the CPU scheduler is. You will force the threads to execute some code in a certain order, regardless of whatever the CPU scheduler will. The CPU scheduler tries to schedule the threads in the opposite order, some threads will have to wait for that turn. So this scheduling constraints are very useful things to use to implement certain tasks, as we will see as well. Yeah. Now, if you are using the threads semaphore to implement scheduling constraint, you will actually initialize the semaphore to 0, not to 1. Okay. And we'll see what that does. So you will then basically you will be able to use this code to do interesting things. And here is an implementation of the join method, or the join system call. What join does is, when you say join, or join is the same as wait PID, okay, which says wait for this thread to process to finish and then continue execution. When we did 4, we saw the wait PID call. So here's a simple implementation of wait fit using semaphore. Okay, so we set the value to 0, and when you call wait PID, you call wait. So you should call wait, this will immediately block the thread. So you set it to 0, it will decrement and return -1. And then you are going to basically block. And then when the thread finishes, you are going to call signal in the exit method. This will wake up this thread, and then it will know that the thread, the process that it was waiting on is finished. So you can use this primitive to do interesting things. In this case, we basically made a thread wait for another thread to finish. So you can use it to do lots of other things as well, as we will see. Okay, let me ask if there are questions, and then I'll show you how to do producers and consumers using semaphores. Okay, which is the first real piece of code that you will see that does some interesting synchronization. Yes.
Wait, I don't really understand the waiting for the thread to finish and then.
Okay. Let me explain what that means again. Okay, so the first thing is to understand what scheduling constraints mean. I'm going to just reiterate what I just said. Let's see if this makes it a little better. So if you have a scenario where you want one thread to wait for another thread to do something, or you want one thread to go after another thread, independent of the way the CPU scheduler schedules this thread, you can use semaphores to do that. Okay? And the way you are going to use semaphores is you are going to initialize the semaphore to 0, and the thread that has to wait for something else to happen is going to call wait, which will call it to block immediately. Okay? Because you set the value to 0, and you call wait, the value goes negative, and you are going to be blocked. And then the other thread, once it finishes whatever event or task it needs to do, it is going to call signal and unblock the first thread. Okay. So this is exactly what is happening here. Thread join and thread finish are just two functions where join and finish simply says that when you call join, you wait for some other thread to finish execution. They be implemented using semaphore. You set the value to 0, and the waiting thread, the thread that needs to wait for the other thread to finish, is going to call join, which will be internally implemented using wait, and it will be blocked because if you set the value to 0. Okay, when the thread that it is waiting on finishes, it is going to call signal internally, okay, and unblock the first thread. Because signal is going to check the values, increment the value, it will check if there are blocked threads, and it will unblock them. And this will cause the first waiting thread to know that the thread has finished execution. Is that any clearer?
So thread.finish is something you call when you finish.
Yes, so basically when a thread terminates, you are going to call this function implicitly or explicitly. This is like the exit call. Okay? And then that will internally be implemented using signal. So this is implementation of it. And this will basically unblock the thread that called the join.
Oh, wait, so you're saying signals inside finish?
Yes, there should be braces there. That's yeah. So that's not two statements. It's basically implementation. So join is simply semaphore.wait and finish is semaphore.signal. So those are the implementations of it. And we will see when we do producers and consumers next the same idea, but you will understand why you have to do what we are doing. Okay? So let's do producers, consumers. We've encountered producers and consumers before. Okay, so this is going to be an implementation of producers and consumers using semaphores. I presume this was not done. It was? I know. We did it using logs. We do it using semaphores. So you can pay some attention to what's going on. Okay. So we are going to now use not one but 3 different semaphores. Okay. So these are the 3 semaphores in your producers, consumers. Okay. You can have arbitrary number of producers and arbitrary number of consumers. General implementation doesn't matter how many threads are producers, how many threads are consumers. For simplicity, let's assume 1 producer and 1 consumer for now, but you can have any number. So we will have 3 semaphores. One is called a mutex semaphore. That semaphore is going to behave like a lock. Okay. Now we need 2 more semaphores. Okay. What do these 2 semaphores do? There's a semaphore called empty, and then there's a semaphore called full. Okay. Why do you need those semaphores? So I hope you all remember what producers and consumers do. First of all, before I go into implementation, let me just reiterate what this is. Okay, so producers and consumers share a buffer, which you can think of as an array or a circular buffer. Your producers that are simply producing data items and they stick it into the buffer. Okay, and there are consumers that are going to consume any data that has been put into the buffer. Okay? The buffer in this case, this is a bounded buffer. This is not an infinite array that can keep growing. The buffer is declared a priori and it has size n. Okay, so that means there are n slots in that shared buffer. Initially, all the slots are empty. Okay? So producers and consumers can run in whatever order they want. Okay? So initially, let's say producer runs, okay? And it starts producing data items. If it goes and fills the buffer up before the consumer has consumed the first data item, okay, then it cannot run anymore. Because if it produces any more data item, there is no place to put it. Okay. Is that clear? So if the buffer is full, which means it's filled with data items, then producers have to block. You cannot run the producer anymore, even if it wishes to produce any more data items. And the opposite is true as well. If your scheduler schedules a consumer before any producer has run and the buffer is empty, there is nothing to consume. Okay. In this case, also the consumer has to block because there is nothing for the consumer to do until a producer gets to run and produce at least one data item. Okay. So your semaphore empty is going to block a consumer whenever the buffer is empty, and the semaphore full is going to block a producer when the buffer is full. Okay, now, how do we do that? We look at the code. I'm just trying to explain the intuition, the design of the producer consumer the solution. Okay. So there are three different semaphores. There is a lock. Why do you need a lock? This is a shared data structure. Only one thread should try to remove or add items to it at any given time. So we are going to protect access to the buffer with a lock. That's a mutex semaphore. That's a binary semaphore. It behaves like a lock. Okay. In addition to this, we have two more semaphores that basically say if the buffer is full, then block the producer. Don't let the producer produce more data items. There's no place to put it. And there's another semaphore that says if the buffer is empty, there's nothing to consume, then block the consumer, wait for the producer to run. Okay. So that's the basic idea. So we will use three semaphores to achieve our goals. There's a mutex semaphore, there's an empty semaphore, and there's a full semaphore. And this is how we initialize them. I said you can initialize them whatever you want. So the mutex semaphore is initialized to 1. Okay. The empty semaphore is initialized to n. Okay. And full semaphore is initialized to 0. Okay. So now the code for the producer is on the right side here, and the code for the consumer is here. So the producer is going to first produce a data item, and then it's going to call wait on empty. Okay. So it's going to say wait on the empty semaphore. Okay. So the empty semaphore is set to n. Okay. Think of it as the number of empty slots you have. Initially, all n slots in that buffer are empty. So it's set to n. So after you produce the first data item, you call a wait. Wait decrements the value, it goes from n to n minus 1. Okay. And that's not negative. So you are going to let the producer do what it wants. So it will grab a lock on the buffer. So it's going to do mutex wait, grab a lock on the buffer, add the item to the buffer, and unlock. Okay. So now we just produced one data item. Okay. So we basically filled this slot. Okay. Okay. Empty is gone to n minus 1. And you decremented it when you called empty.wait. Okay. No consumer has run yet. So full is still 0. Okay. That's the value initialized. But the producer at this point can run n minus 1 more times because there are n minus 1 more slots. Each time we call empty.wait, will decrement the value. Can we keep filling this slot? If the scheduler schedules these threads such that the producer runs for a long time and it keeps producing data item, it will fill the buffer. The scheduler can do whatever it wants. Okay? The code is corrected, so the code is not going to depend on what our CPU scheduler is. Okay? Our code is going to control what is the right thing to do. Now let's take the other scenario. Okay? So it should be clear how these work. So I'm going to say before the producer ran, let's say the CPU scheduler just runs the consumer thread. And we'll see what happens. Yes?
So what does wait do besides decrement do the semaphore?
What does wait do besides decrement? So what wait is going to do is it's going to decrement, it's going to check the value. If the value has been decremented to negative, it will block the thread that called wait. Okay. So this is a thing you should keep in mind. Always decrement, value goes negative, block. The value is non-negative, continue execution, no blocking. Okay. The release signal is the opposite. You increment, and now if the value is less than or equal to 0, unblock any thread that was waiting. Okay. So that's basically what it's going to do. So we are simply going to keep this implementation in mind as we go through producers and consumers. Okay. So here the example I just get, did a wait here, it decremented it, we checked the value was non-zero, so there was nothing to do, there was nothing to block, so we let the producer continue. Okay, if the producer had produced n data items and filled up this buffer, this value would have gone to 0, and as it tries to produce the n plus first data item, you will again call wait, it will make wait go minus 1, at that point the producer will be blocked, it will be put on the queue as per our implementation. So it will not be able to add that data item to the buffer because the buffer is full. Okay, is that clear? Okay, so now let's look at, it's clear, you can tell me how the consumer works. Okay, let's assume first that the consumer ran before the producer could run at all. Okay, the buffer is completely empty. You should look at the code and see what is going on. First statement says to do a wait on full. Okay, so what does that do? Yes. Okay. So it's going to get blocked right away. Okay. And you should understand why, both at the code level and the intuitive level. The first thing is it should get blocked because the buffer is empty, there's nothing to consume. The consumer just happened to execute first, and there's nothing to consume, so it should be blocked until the producer gets it. So at the intuitive level, you should realize that if the producer runs whenever the buffer is empty, you block. Now look at the code and convince yourself the code actually blocks the consumer. Okay, so you call the statement here. You call wait on full. What's the value of full? Okay, so you see that it's 0 there. That's what the initial idea. So wait decrements. Okay, value went negative, -1. Okay. What does the implementation of wait do when the value goes negative? Okay, so it's a value less than 0, which it is. It's gone negative. You basically block the process. Okay, you put it on a queue and you block it. Okay, so that's essentially what's going to happen to the consumer. Consumer will get blocked. Okay, so now let's take the scenario. Consumer ran first, got blocked. The producer runs next and produces a data item. What happens in this case? We look at the code completely. Okay. So let's go back to the producer code. Okay. So now the scenario is this is -1. Okay. Consumer is blocked. Okay, because consumer ran first, it decremented, value went negative, consumer is blocked. Now the producer runs. Okay. So it's going to execute the same code we looked at. Okay, first it's going to do a wait here. So this is going to go n-1. You produce a data item. Okay, you'll add it to the buffer. Okay, and then you should see what else it is doing. If you look at the last part, you're going to basically release the blue text by saying blue text or signal, so you unblock the buffer, and then you call a signal on full. Okay, so what does signal on full do? What will signal do first? Okay, it's going to increment the value. So what is the value of full? It's negative. So it's going to increment it. Value will go to 0. Okay, that's not all of what it does. Yes. Yeah, so it's incremented. Exactly as I said, it's going to now check the value. Value is 0, it says value less than or equal to 0. It's 0 currently. So you're going to go and look at the queue, okay, and pull the process or thread that was waiting on the queue. That's this thread here. It was blocked, it was put on the queue. So you unblock it. Okay? So now this will become ready to run again. Okay? This value is 0. Now next time the consumer runs, it's going to execute the same code again. Okay. Now this time, basically there's a data item that you can consume, so you shouldn't be blocked. So you can consume this data item. Okay. So intuitively at this point, so at the intuitive level, once you produce the data item and the consumer runs, you shouldn't block. First time it ran, there's nothing in the buffer, so you block. This time you run, yeah, well, you can unblock, so subsequently you get scheduled to run, you shouldn't be blocked. Okay? So let's look at the code again and see what happens. Okay, so you are going to call full.wait, and then you are going to call new text. So once the value was 0, it was negative and it's incremented again. So you call signal. Okay, so you are called signal. So what happens in signal is the consumer was blocked within wait. If you remember, when you had called wait the first time, you are blocked here. Okay? The signal here has unblocked it, so you come out of wait. Okay, so the thread that was blocked has now gone past wait and it's now here. So it's going to continue execution. The thread that has become ready is going to come out of wait, continue execution, is going to grab the lock on the buffer, okay, and then it's going to consume this data. and then you're done. And then you're basically going to continue. Okay. Something.
Is each semaphore on its own queue?
Each semaphore has its own queue. So there are 3 semaphores here. Okay. Wait has its queue. So this semaphore has a queue. This semaphore has a queue. Mutex will also have a queue. Okay. So the consumer semaphore is going to be put here. The producer threads will be put here. Okay. If you produced n data items and it was full, then this will go to 0 and you'll put your survey. Okay. So is that clear? So we'll stop here for today and continue this next time.